Welcome to this video series on how to design an impact wrench adapter for use with a cordless drill. In the previous video we listed the design requirements, explained the physical principles of how an impact wrench works and shows the mechanism that we will be using for our design. In this video we will be covering the dynamical calculations that are necessary to determine the size of the flywheel. This will include solving a dynamical model in MATLAB Simulink. After that, we will also cover the calculations that are needed for dimensioning the V-grooves, shaft and spring. So the first step is setting up a dynamical model to determine the optimal flywheel hammer dimensions. Remember that we want maximum kinetic energy at impact for maximum output torque, but we will also have to take the duty cycles of the DC drill motor and the impact rate or IPM into consideration, even though this was not listed in the original design requirements. Most cordless impact wrenches have an impact rate between 1750 and 4200 impacts per minute, so being within this range seems reasonable for this design. Here we again see a typical DC motor torque speed curve from the website of ISL products. This graph also shows the torque or speed ranges for the different duty cycles. Rules of thumb are continuous usage between 0 and 30% of the stall torque, intermittent usage between 30 and 60%, and the danger zone is above 60% of the rated torque, as the motor will overheat quickly. To not risk damage to the drill, we must keep the time within the danger zone to a minimum by ensuring that the flywheel can accelerate fast enough to the RPM in the intermittent or continuous usage range. Now, recall Newton's second law of motion for rotation and the rotational kinetic energy equation as mentioned in the first video. Torque is equal to the mass moment of inertia times the angular acceleration. And the rotational kinetic energy is equal to 1 over 2 times the mass moment of inertia times the angular velocity squared. If we want to calculate the angular velocity at impact, we need to integrate the angular acceleration over time. When we rewrite the first equation, we get that the angular acceleration is equal to the torque divided by the mass moment of inertia. The mass moment of inertia of the flywheel hammer is a constant, so the angular acceleration varies with the torque provided by the motor and the friction. The friction torque is neglected, so we assume that the net torque is the same as the torque delivered by the drill. The torque provided by the motor of the cordless drill changes linearly with the rotational speed, as has been shown previously. If we write torque as a function of the angular velocity, we have to derive a linear equation. We know from the torque speed curve that the motor provides maximum torque at 0 RPM and 0 torque at maximum RPM. The derived equation is that the motor torque is equal to the stall torque minus the stall torque divided by the no-load speed, times the actual speed. From the specifications of the cordless drill we know that the stall torque of the drill is 12.5 Newton meters and that the no-load speed is 1500 RPM. Filling in these values gives us the torque equation for this specific motor. If we go back and substitute the equation for torque in the equation for acceleration, we can see that the angular acceleration is dependent on the angular velocity and vice versa. To solve this, we first need to write this down as a differential equation. The angular velocity is the derivative of the rotation angle. The angular acceleration is the derivative of the angular velocity and thus the second derivative of the rotation angle. The notation we use is 1 dot for the first derivative and 2 dots for the second derivative, so the differential equation looks like this. Note that a constant is added into the equation to convert from radians per second to RPM. The only variable that is not yet specified in the differential equation is the mass moment of inertia. This is the total mass moment of inertia that the torque of the motor has to accelerate, which include the flywheel hammer and the drive shaft. In this early design phase, we only consider the mass moment of inertia of the flywheel hammer and neglect the drive shaft. For now we assume the flywheel to be a solid cylinder, so the mass moment of inertia is equal to 1 over 2 times the mass of the flywheel times the radius squared. The mass of the flywheel is calculated by multiplying the volume with the density of the material. The material I am going to use for the flywheel is steel, since this has a high density of approximately 7,850 kilograms per cubic meter, is relatively cheap and has good strength properties. The volume of a solid cylinder is pi times the radius squared multiplied with the length. There are now two variables that can be varied, the diameter and the length of the flywheel. Choosing a larger diameter is the most effective way to increase the mass moment of inertia while keeping down the weight, but remember that the diameter and length of the flywheel are both limited by the requirements. The adapter is limited to a total weight of 2 kilograms and a diameter of 80 millimeters. Considering that the maximum diameter of the adapter including the housing is to be 80 millimeters, an initial diameter of 60 millimeters is chosen for the flywheel. To choose an optimal length for the flywheel, we have to go back to the differential equation. Remember that we want maximum kinetic energy at impact and that the maximum speed of the drill motor is 1,500 rpm. Choosing a flywheel length such that the angular velocity can still reach 1,500 rpm at impact, which is after 1/2 rotation or 180 degrees, is most effective as the velocity is squared in the equation. This does not necessarily result in maximum kinetic energy, but we also have to take the mass limit, the duty cycle of the drill and the impact rate into consideration. Now that we have set the target, let's solve the differential equation with different flywheel lengths. In MATLAB we start Simulink so we can implement the differential equation in a block scheme with math operations. First we have a look at all the constant parameters in the differential equation for which we insert the constant blocks. The constants are the no-load speed, the stall torque, the density of the material, the diameter of the flywheel and the length of the flywheel. For each constant we also fill in the correct value. For the calculation we convert everything into SI units before the math operations, so millimeters become meters and RPM become radians per second. We do this with gain blocks, which multiplies the input with the gain value or in this case, the conversion factor. The conversion factor for RPM to radians per second is 2 times pi over 60 or pi over 30. The conversion factor for millimeters to meters is 1 over 1,000. The radius of the flywheel is to the power of 4 in the differential equation, which is achieved with a power block and a constant block with a value of 4. The equation for the mass moment of inertia is then calculated with a product block which multiplies all the inputs. An additional constant block is created for half times pi in the equation. In the next step, a product block is used to divide the stall torque by the mass moment of inertia as shown in the differential equation. The output is the input for the next product block, where it is divided by the no-load speed for the second part of the differential equation, so this can later be multiplied with the actual speed. A sum block is used to subtract the second part of the differential equation from the first part. A product block is added to multiply the second part of the differential equation with the actual speed, which is left open for now. The output result from the add block is the angular acceleration. We use an integrator block to obtain the angular velocity, and an additional integrator block is used to obtain the rotation angle from the velocity. The angular velocity is the actual speed here and can be used as input for the product block to close the loop of the differential equation. We want to evaluate the RPM and the kinetic energy of the flywheel at a half rotation, so again we use a gain block to convert the rotation angle from radians to the amount of rotations, and also to convert the angular velocity back from radians per second to RPM. At the end, we place a scope block with 3 input values to view the results in a time graph after running the simulation. We still have to implement the rotational kinetic energy equation in the block scheme. We do this by adding a constant block and a square block with the velocity as input and the mass moment of inertia to the product block. The output then also goes into the scope block. There is one last thing we can add to make reviewing the results more user-friendly. We are only interested in the speed and kinetic energy at a half rotation, so if the simulation automatically stops after a half rotation, we can just evaluate the results at the time the simulation has stopped. We can do this with a stop simulation block in combination with an if block. If the input, which is the numbers of rotations, is equal to or more than 0.5, then the if statement is true. We must add an if action subsystem block to execute an action if the statement is true. We add a stop simulation block at the output, which will stop the simulation if the input is non-zero. Therefore, we add a constant of 1 as input to the if action subsystem. The first simulation is done with flywheel length of 50 mm. We can now run the simulation by specifying the stop time and clicking the Run button. To view the results, we can double-click on the scope block. If we click on the scale X and Y axis limit button here, we get the complete graph. Let's click on View and select Legend to see which curves are the kinetic energy and RPM. With the Zoom Y button, we can zoom in on the Y-axis to view the result more precisely. The maximum speed for a flywheel length of 50 mm is about 1477 RPM. The kinetic energy at impact is approximately 6 joules. Now we reduce the flywheel length by 20 mm to a length of 30 mm and run the simulation again. If we zoom in on the speed, it shows a maximum of 1497 RPM, which is almost the limit. The kinetic energy is about 3.7 joules, which is less than the first simulation. We now increase the flywheel length by 20 mm to a length of 70 mm and run the simulation for the last time. The maximum speed has reduced to 1441 RPM. Still, the kinetic energy has increased to almost 8 joules. We can also check at which time the simulations ended in the graph, so you know the time it takes for each impact. By dividing 60 with this simulation time, you can obtain the impact rate in number of impacts per minute. In the graph you can also check the time within a certain speed range. This is useful for checking the time within the danger zone for the motor. An easy way of doing this is changing the if statement in the block scheme, so the simulation will stop when the maximum speed inside the danger zone is reached. This is at 40% of the no-load speed, so 600 RPM in this case. Then we again check the time at which the simulation ended. I have run simulations for flywheel lengths from 10 mm up to 70 mm with steps of 10 mm, and the results are listed in this table. Notice that the kinetic energy increases and the impact rate decreases almost linearly with mass within this range, because the difference in impact speed is almost negligible. There is no obvious flywheel length that would perform best considering all factors. Purely based on impact energy, a larger flywheel would be best and the impact rate would still be within the desired range. There is a weight limit of 2 kilograms, but we don't know the weight of the other parts yet, so it is best to be conservative here and have some margin. We also want minimal time in the danger zone to prevent overheating of the drill motor. A flywheel length of 30 mm seems like a reasonable trade-off, which can still be changed later in the design if necessary. We can now continue to the other calculations. The spring, the diameter of the driveshaft, and the angle of the V-grooves need to be chosen correctly to ensure smooth operation without any malfunctioning of the mechanism. In other words, if rotation of the hammer is blocked by the anvil, the motor torque must be able to overcome the spring force with the ball and the angled groove and retract the hammer from the anvil. The spring must also not be too flexible, as this will cause the hammer to retract too far, causing the balls to lock or the hammer to return too slowly for the next impact. First, we draw a free body diagram like the one shown here to get a clear picture of the forces involved in the calculation. In orange we see the forces on the ball due to the compression of the spring and the tangential force from the motor torque. In blue we see the resultant normal force perpendicular to the groove and the net force parallel to the groove. We also need to define which directions are positive, which is also shown in the free body diagram. If the net force is positive, then the hammer is retracted, and if the net force is negative, then the hammer returns onto the anvil. We must calculate the forces in orange before we can calculate the net force, which we are most interested in. The spring force is calculated with the spring constant and the deflection of the spring. The maximum deflection of the spring depends on the preload and the retraction distance of the hammer from the anvil. The tangential force is calculated by dividing the motor stall torque by the radius of the driveshaft. The net force is then equal to the tangential force times the cosine of the groove angle alpha minus the spring force times the sine of the groove angle alpha. The normal force can be used to calculate the friction force due to the rolling resistance of the balls. We won't include friction in this calculation since the contribution is minimal and therefore negligible. To summarize, we have to decide on the following combination of parameters: the diameter of the drive shaft, the angle alpha of the V-grooves, the retraction of the hammer, the preload of the spring, and the stiffness of the spring. I made an Excel sheet for calculating the forces that are shown in the free body diagram. With this Excel sheet we can easily vary the combination of parameters to get to the desired result. First we write down all the names of the input and output parameters before filling in a value or formula. To make a distinction between the input and output parameters, we make the input cells orange and the output cells gray. In the orange cells we list the input values that I initially chose for my design. We already know the stall torque of the drill is 12.5 Newton-meter. I chose a shaft diameter of 20 millimeters. The hammer height is 8 millimeters, so the retraction must also be 8 millimeters. The ball diameter is 5 millimeters. This is relevant for calculating the minimum required deflection of the spring. Initially we assume a groove angle of 45 degrees. Before filling in the parameters of the spring, we first write down the formulas in the gray output cells. These are the formulas that were shown earlier for calculating the tangential force, the compressed spring force, and the net force. For the net force we make a distinction between the initial net force due to the preload of the spring and the retracted net force when the spring is compressed after hammer retraction. Let's also add the formula for calculating the minimum required spring deflection for assembly. This is simply the sum of preload deflection, the hammer retraction, and the ball diameter. The spring force for assembly can now also be calculated by simply multiplying the spring constant with the required deflection. Now it is time to select a spring so we can fill in the spring constant and check what the value for net force is and whether the spring has the minimum required deflection. We can also play around with the groove angle and the spring preload to achieve the desired net force. There are several combinations possible, but I wanted to limit the spring force to about 500 Newton for safety reasons, and I also wanted to keep the spring length to a minimum. When searching for a suitable spring, we limit the inner diameter from 20 to 25 millimeters. Now we can sort the springs on length. When scrolling through the springs, we keep an eye on the maximum spring force and the difference between the free length and the compressed length. This spring seems reasonable, so we fill in the parameters in the Excel sheet. The listed spring constant is 21.12 Newton per millimeter and the compressible length is 26.4 millimeters. Besides the spring constant, we also have to define the preload. The limit for the preload depends on the available spring deflection and spring constant. If we fill in a preload of 210 Newton, we can see that the minimum required spring deflection is 22.9 millimeters of the available 26.4 millimeters, so we could increase the preload to about 270 Newton. Instead, I chose to increase the groove angle up until the point where the retracted net force is a little over 100 Newton, which is 68 degrees. To summarize, in this video we decided on the following: a flywheel diameter of 60 mm and a length of 30 mm. A drive shaft diameter of 20 mm. A hammer height and retraction of 8 mm. A groove angle of 68 degrees. A ball diameter of 5 mm. And we selected a spring with a preload of 210 Newton corresponding to 10 mm deflection. In the next video, the 3D parts will be modeled in Siemens NX according to the results of this video. We will also be selecting the bearings and then combining everything into an assembly. From the 3D CAD models, we will be making the 2D drawings and extract the other files required for production.